Hello there. Welcome to the third lecture of our module 3, and in this lecture we will cover mainly that descriptor of random variables. And in the last class we stopped somewhere at while we have started description of the CDF, that is cumulative distribution function. So what we will do, we will start with that CDF, the description of the CDF, and we will see some problems on it. Particularly pure CDF, and we will also see some example of the mixed variable where some part is discrete and some part is continuous. We will see one such example, and then we will go to some general descriptors of random variable. So, where you stop in the last class is the description of the CDF for a discrete random variable. We know that there are two types of random variable, one is discrete and another one is continuous, and for both these type of variables we have seen what is their density function, that is probability density function for continuous random variable and probability mass function for discrete random variable. So, now we are starting that CDF, that is cumulative distribution function for a discrete random variable. So, for a discrete random variable, the CDF, that is Pxx, is the obtained by summing over the values of PMF, it is probability mass function. For a discrete random variable, the CDF Pxx is the sum of the probabilities of all possible values of x that are less than or equal to the argument x. So, if this notation, that is Pxx, stands for the CDF, the values of the CDF at x, which is nothing but the summation of their PMFs for all possible x which is less than this small x. Now, this is the, so if we take the one our standard example of throwing a dice and getting that 6 different outcome 1 to up to 6, and if we say that all these are equally likely, then the PMF says that at exactly at the point for exactly for the outcome 1, the probability is 1 by 6, and for all such outcomes the probability is 1 by 6. So, this is now concentrated. So, in the last one we have seen that its PMF looks like this, where this 1, 2, 3, 4, 5 and 6, and all are the concentrated mass, and these are all equal up to 1 by 6. Basically, this should be the representation of this PMF, and in some book you will see there is a stem diagram or kind of that, but this is, as we are telling that these are the concentrated mass of probability, that is why the name PMF. So, these dots are sufficient to declare that this is a PMF, but just for the reference we can just put one dotted line like this, just to indicate that this is referring to that particular outcome. Now, if I want to know what is the CDF for this kind of descriptor, then you see that there is some two important thing that we should keep in mind. The first one, that is, if I just take this reference line for this one, so this point is 1 by 6. Now, for if I want to know what is the value for this 2, then I know that for 2 this will be exactly 2 by 6 or 1 by 3. So, this probability, when it is exactly equal to 2, then it comes, the probability comes to be 2 by 6. Now, what about for this line in between some number? Now for the CDF, I can say that any number, the argument can take any number between 1 and 2, then less than that value, say for example 1.75. So, what is the cumulative probability up to 1.75? Then obviously the probability is 1 by 6. So, the probability that CDF remain constant starting from this 1 and going up to 2. Now, as soon as it touches 2, it shoots to 2 by 6. So, generally in the representation we should not touch the line of 2. So, this is a continuous line, it will simply start from 1 and go as close as it can go up to 2, but it should not touch 2. immediately when it touches 2, that is the cumulative probability at 2, that is less than equals to, that is why the less than and equal to, that is why here the probability distribution function value of the CDF, that is the cumulative distribution function value of CDF at 2, it is 2 by 6. Similarly, so it will be one line and it can go as close at it as it can up to 3, but it should not touch the line 3. So here, so like this, so basically we are getting some lines, continuous lines as step lines like this, and it is going up to 1. So this should be the representation. So this is very important, that it can go as close as to the next value, but as soon as it is touching the next value, there is a sudden jump of this one. So this kind of step function that we can see for a discrete random variable, that representation of cumulative distribution function for a discrete random variable. So in this figure you can see there are some these steps are shown, and there is, so this line cannot touch this line, and these dotted lines are nothing, just the representative, just to show that this point corresponds to exactly equals to 2. So this CDF is represented only by some straight line parallel to the x axis in this 6 different steps, and finally which is touching to that 1. Okay. So this is the representation of the CDF for a discrete random variable. Similarly, if we see the CDF for a continuous random variable, where we know that this particular function, that probability density function that we discussed in last class, where it is having a continuous distribution over the entire support of the x. So if we take that, now if we want to know the value of the CDF at a particular attribute equal to x, that means this fx x, that means the total value up to that particular point we have to see. So here if we see that for a continuous random variable, this maybe the distribution looks like this. So now at a particular value here, if it is x, then this value, if I want to draw that CDF here now, so at this value, this point represents the total area from the left support up to that point x. So this value represents this one. So this will be a monotonically increasing function which will go and touch up to the maximum value that it can take is 1, and it should start from 0. So this value is nothing but the integration, that means the total area of this function up to that point, that means the integration of that function from the left support to that particular point. This is exactly mathematically represented here, that you can see that fx equals to from this minus infinity to that particular point, integration of that that is PDF, probability density function, and this will give you the CDF of a continuous random variable. One thing is important here, once again I am repeating the fact that this one will not give you the direct probability. So this is the representation of the probability density at a particular point, but not the probability. But this function at that point, it is representing the probability of x being less than equals to small x, that particular value. So if from this one, again mathematically we can, if we just take the differentiation of this CDF, cumulative distribution function, then we will end up to that probability density function. Now we will see two examples of CDF. The first one is straightforward, one example of this exponential distribution. The time between two successive events of railway accident can be expressed as this probability density function fxx equals to lambda e power minus lambda x, which is the support is declared as from 0 to infinity. So where lambda is called the parameter which is estimated to a point 2. So these are the parameters, it is estimated from, we will just see in the successive classes how to estimate the parameters of the distribution. So this, with this parameter lambda equals to 0.2, we have to find out what is the probability of the time between two successive events of rail accident exceeding 10 units. Suppose that units is not specifically mentioned here. So, it's a 10 units. What is the probability that two successive events of rail accident will exceed 10 units? So, first of all, what we have to do from this probability density function, we can directly get it from this integration. Now, if we want to know that what is this probability, what is the cumulative density function of this one, we know that we have to integrate this probability density function from this minus infinity to x. So, here it is from minus infinity to 0, it is 0. So, from 0 to x we will integrate it. So, to get that, so if we do this simple integration, we will get this 1 minus e power minus lambda x, which is the cumulative distribution function for this probability density function. Now, if we put any particular value of x here, that means we are we are directly getting the probability of the random variable x being less than equal to small x. Now, our question is find the probability of the time between two successive events of the rail accident exceeding 10 units. Now, it is given that exceeding 10 units, that means if I put here 10, that means I will get the probability of non exceeding 10 units. So, if I want to calculate the exceeding, then the total probability we know 1. So, we have to deduct that particular value from the total probability to get what is the probability of exceeding 10 units. Exactly the same thing has done here, that is probability of the exceeding 10 units is equals to probability x greater than equal to 10. So, x greater than equal to 10 is nothing but 1 minus x less than equals to 10, and x probability x less than equals to 10 is nothing but fx 10. So, this fx 10 we are directly getting from this our probability density function. This will be minus, means after taking out this bracket, this will obviously become plus. So, this is eventually coming to this, after putting this value of this lambda, this will eventually come e power minus 10 multiplied by 0.2, that is the value of lambda. So, this will be minus if we are putting this parenthesis. So, if we take out this parenthesis, obviously this will be the plus, so which is shown it here. So, the probability is 0.135. So, 13.5% it is probability is that the railway accident, sorry, this will be railway accident exceeding 10 units for a particular for that case is 0.135. Now, if we want to see how it is distributed, this, so here that probability density function is shown and this probability that cumulative density function is shown. Now, if we want to see how it is varying over this x, then this is the graph. So, you see here, so at x equals to 0, the value of this probability density function is 0.2 obviously, which is the value of lambda, and gradually as it goes to infinity, you see it is coming down and being asymptotic to the value 0. Now, if I want to get that CDF, that means this CDF is this one. So, that CDF will be nothing but the integration of this area. So, gradually that integration will increase and it starts from 0 and will be asymptotic to the value 1, and it will be 1 at x equals to infinity. So, this curve that you see, this is your CDF and this one, this is your PDF for the exponential. This is the typical example of the exponential distribution that we showed you in the last class. So, these are how this PDF and CDF for this case looks like. Another interesting problem is taken here. This is on this daily rainfall at a rain gauge station. Assume that the daily rainfall at a rain gauge station follow the following distribution. Now, the daily rainfall if we take from a particular station, then what we see that in most of the time there will be many zero values, and for some non-zero values it will come. So, what is done is first of all we just collect that reading, and in that reading we get some non-zero values, say 1, 2.1 like this we will get, and then we get many zeros and again some value 0.1 and so. So, what is meant is that this daily rainfall value or that kind of value is the series is having many zero values. So, if we want to calculate those probability distribution function, what we generally do is that we generally exclude this 0 value first, and we see what is the probability of getting the value 0, and then we fit the another probability distribution for this non-zero value. So this is one example of the mixed distribution, where at 0 there is some probability is concentrated. So if we see this one, so at 0, if it is 0, at 0 some probability is concentrated here, and for this non-zero values it may have some distribution. And obviously the more the magnitude of rainfall depth, obviously the density will come down. So this is one example of, so here some probability is concentrated here and it is coming up. So now you can see that at 0, if some value is concentrated here, so the total area under this graph obviously will be 1 minus what is this value, what is this value concentrated as at 0. Okay. So this example we have just we have considered here, and we have just taken one example, that this Fx equals to, here you see that 40% probability is concentrated at x equals to 0. So now that for x greater than 0, the CDF is c e power minus x by 4, and elsewhere it is 0, that is from minus infinity to less than 0, this value is 0. So this is the complete description of the CDF, and this is example of a mixed distribution where there is a probability mass here concentrated at 0 and a continuous distribution for greater than 0 values. So first we have to find out C, and then we have to answer that what is the probability of daily rainfall exceeding 10 centimeter. Okay. So this x is having the unit of centimeter here. So first what we have to do, so find out C. So C is a constant here. So if we have to find out the proper value of C, that means the total area under this curve should be equals to 1. That thing we have to satisfy. So it is done. So from the minus infinity to plus infinity, from the second axiom of probability, we know that this total, so the condition of this PDF, that this total integration should be equals to 1. Now I know that from minus infinity to less than 0, the value is obviously 0. From at 0, the concentrated probability mass is 0.4, and from 0 to infinity, this that function we know, and this should be equals to 0. So if we just do this integration and solve this equation for this one unknown here, so we'll, after doing some step, you will get that C equals to 0.15. So the value of C we got. So so the complete description of this probability distribution will be Fx x equals to 0.4 for x equals to 0 is equals to 0.15 e power minus x by 4 for x greater than 0 and 0 elsewhere. So here it is written that for x equals to 0, that now if I want to get the CDF, that cumulative distribution function for x equals to 0, this Fx x, that is x exactly equals to 0, equals to 0.4. Now for this range, that is x greater than 0, Fx x, which is nothing but the probability x less than equals to 0, is should be equals to that concentrated mass at x equals to 0, 0.4, plus the integration from 0 to that particular point x of this function. So if we do this few steps, we will get the distribution function as that for this x greater than 0 in this zone is 1 minus 0.6 e power minus x. Now once we get this CDF, then the rest of whatever the answers we are looking for, that is, for example, here we are looking the answer for this x greater than 10 centimeter. So so this is the final representation of this CDF, that is Fx equals to 0.4 for x equals to 0, 1 minus 0.6 e power 2.5 x is greater than 0 and 0 elsewhere. So this will be 0.25 x. So instead of minus x, this will be 0.25 x. This is the correction here needed. So this, with this final form of this CDF that we got, now we will put that x is x equals to 10 to get that the probability here it is asking what is the probability that rainfall, again here it is shown that exceeding 10 centimeters. So, we will first calculate the probability from this CDF, what is that probability of this daily rainfall less than equals to 10 centimeter, then from total probability 1 if we just deduct we will get that answer. So, from this one if we just put that x less than equals to 10, that is fx equals to 10, which is nothing but 1 minus this equation 0.9507 we will get from this one. So, the probability of daily rainfall exceeding 10 centimeter obviously will be is greater than 1. So, 1 minus probability x less than 10 is equals to 0.0493 is this probability. So, up to this what we have seen is that we have just seen that PMF which is for the discrete random variable, that is probability mass function. Then we have seen that probability density function which is for the continuous random variable, and last we discuss about this cumulative distribution function for both discrete and continuous random variables. So, some notes here on this, the probability mass function PMF is the probability distribution of a discrete random variable. The probability density function PDF is the probability distribution of a continuous random variable. Cumulative distribution function is the non-exceedance probability, probability of a random variable, and its range is between 0 and 1. So, now the main descriptor. So, now sometimes if we do not get any particular closed form of that closed form of this probability density function or probability mass function of a variable, then from the observed data there are some descriptors of this random variable that we will see. So, that approximately with these descriptors a random variable, the nature of a random variable can be known to us. So, this is our next focus, to know that what are the different main descriptors of a random variable. So, what we will see that what is meant by this descriptors of random variable, that we will see first, then we will know what is mean or the expected value, then variance or the variance and standard deviation, then skewness, then one more is there for called the kurtosis, and then we will also see the analogy with the properties of the area, that is area under the PDF probability density function in terms of in case of the continuous random variable, that we will see, just to relate that how this thing can be called as a moment, and that we will see. So, probabilistic description of random variable, if we want to see, take some random observation of a random variable, some random sample data if we take, then we can see these things, that is the probabilistic characteristics of a random variable can be described completely if the form of the distribution function PDF or PMF is known, obviously what we discussed so far, and the associated parameters are specified. For example, that for the exponential distribution, that lambda e power minus lambda x, so that lambda is the parameter. So, if we know that what is that density function PDF, that is it is exponential form, and if we know the value of lambda, then it is completely known to us, that the total distribution is given to us. So, this is what is it is meant by this point. Now, in the real life scenarios where the nature of the distribution function of the random variable is not known, an approximate description becomes necessary. The approximate description of the probabilistic characteristics of the random variable can be given in terms of the main descriptors of the random variable. So, this is why. So, if we do not know the exactly the closed form of this equation, this is why this main descriptors becomes very important, just to know the nature of the distribution of that particular random variable. So, there are the first 4 description that we that are very important, and obviously there are higher side, but this first 4 is very is important and mainly is responsible for the nature of this distribution. The first one is the measure of central tendency. This measure of central tendency means where the center is. Now, this center is again a subjective word, means in what sense we are looking for the center. So, given a random variable, given the distribution where its center is, that can be, there are three different ways that we can say that what is the its central tendency. Second thing is the measure of dispersion, how, so about that central point, how the distribution is dispersed, how it is spread around that particular central value. Then measure of skewness, whether there is any skewed, whether it is skewed, whether it is symmetric. So this is a measure of symmetry, you can say that whether it is symmetrical or has some skewness to either to the left or right of this central point. And measure of peakedness, so whether the peak of that distribution is very high or low, like that. So we will go one after another. We will start with this measure of central tendency. The central value of a random variable. So within the range of the possible values of a random variable, the different values are associated with different probability density. So the central value cannot generally be expressed in terms of the midpoint of the possible range. So just for a small thing, if we just say that, if we say that, if we just take that particular example, say if I take the example of the discrete random variable first, for the dice we have seen that 1, 2, 3, 4, 5, and if I 6, and if I say that all these things are equiprobable, then we can say that central is somewhere around 3.5, the outcome central tendency is 3.5. Now think in the situation where these outcomes are not equally likely. So the mass is concentrated, 1 is from for here, for 2 it is here, 3 it is here, 4 it is here. So if it is like this, then it may not be, that that midpoint of this outcome may not be the central tendency of this one. Obviously when I am putting this dot, obviously I have kept in mind that the summation of all this should be equals to 1. Those axioms, what I mean is that obviously after satisfying all the axioms that is needed, before I can declare that this is a valid PMF. So if the what here it is understood, the central tendency is that the central tendency need not be always to the midpoint of the observation that we see. It depends on this, how much density is associated to each outcome of that particular random variable. Okay, so this is what is meant for this central tendency, and there are three different ways how we can say, how we can express that. The first, the central value of the random variable can be expressed in terms of three quantities. The first is the mean or expected value, second is mode, and third one is median. So we'll see the mean first, which is expected value as well of the random variable. The mean value or the expected value of a random variable is the weighted average of the different values of the random variable based on their associated probabilities. For a discrete random variable x with PMF Px xi, the expected value is Ex is equals to xi multiplied by that associated probability. So instead of just simply calling that this the average of this, so the average of this outcome, where what we are doing is that we are just taking the weighted sum, the weighted average, the average is taken by the weightage of the associated probability. So this is the expected value. Now instead of multiplying the same values here, that is the same values, that is 1/6 for each and every outcome, I am multiplying each outcome by their weighted probability. So this may be something, but when I am putting the weight for these two, this is obviously very high. So obviously the central tendency will pull that central part towards this particular observation, because here the probability, the concentration, the mass is very high compared to the other outcome. Now taking this same concept for this continuous random variable, that for the continuous random variable x with PDF fx x, the expected value is that for the full range of this random, for the full support of the random variable x, that multiplied by x gives you that particular expected value of that random variable x. We will just discuss in a minute how this is related to some kind of moment. We will just come in that point a little later. So, as we have seen that for when we are talking about the expected value of that particular random variable, then we are multiplying that variable with that particular value, only with that x, or here the outcome, the x. Now, the expected value, instead of we can get the expected value of any function of the random variable. The function of the random variable will be discussed in subsequent classes, but here instead of only, it is what we are trying to say here is that, so that expected value can be obtained for any other functions of that random variable as well, simply by replacing this x by that function and this here x by that particular function. So, here this gx, here this gx is a function of the random variable x. Then when x is discrete, obviously we have to go for this summation, multiplying that gx with that individual masses, the probability mass for that particular outcome, and when x is continuous, then we are taking the integration, instead of multiplying only by x, we are multiplying by this function, that is gx into fxx dx. So, we get that expected value of that random variable, of the function of that random variable gx. Now, there are, so if we know that probability density function, then we can calculate that that mean. Now, if we have some observations, then from the observations, if we want to get what is that sample estimate, now there are different criteria before I declare that this is a particular estimator of that particular variable, that will be discussed later. Those are known as that consistency, unbiasedness. So, this thing, after satisfying those things, if we have the different observation for a particular random variable, then the mean of that particular random variable can be expressed as this, where this n is the total number of observation is taken for the random variable. So, sum it up and then divided by this total number of observation, that what you get, that is the mean of that, the sample mean of that observation, of that sample. The other two measure of central tendency is mode and median of the random variable. The mode says that the mode is the most probable value of the random variable. So, out of the different outcome in case of the discrete and for this overall range, where which one is the most probable value for this one, and this is the value of the random variable with the highest probability density. Obviously, when we are calling this probability density, this is for the continuous. So, if you say this one, so we see that here at 2, that the probability that mass is concentration maximum at 2. So, obviously, the mode here is 2. Now, and for, if I just say that this is your, this is a some probability distribution function, then obviously at this point where you see the density is maximum, this is your mode. Again, if you see that there are some valleys and there are some peak, so there may be some other things. So, these are generally known as the bimodal or multimodal. So, this is having more than one mode. So, this is the secondary mode here, where there is a secondary peak. For example, the standard normal distribution, if you see, this is unimodal and the mode is here at 0. And we will see that, or this that this mean, mode and median is same for this kind of symmetric distribution, that is a normal distribution, this is same, that we will see later. What we are mean here is that for the discrete random variable, where the probability mass is the maximum, that is your mode, and where the probability density is maximum, that is your mode for that random variable. And then it is median. The median is the value of the random variable at which the values on both sides of it are equally probable. if the xm is the median of a random variable x, then fx xm is equals to 0.5. Now this is one thing that where, so when, okay, we will discuss this one first. For in case of the continuous random variable, so I am just started going on integrating from its left support. If it is minus infinity, from the minus infinity I am going on integrating, and I will stop at some point where the total area covered is equals to 0.5. So that means this is the point where the probability less than that particular value is 0.5, greater than that particular value is 0.5. So this value is your median. Similarly, we will go on add up these probabilities, and where it will touch that 0.555 for that corresponding CDF, that particular value. So if we will just add this plus this, so where it will touch that 0.5, that particular value will be the median for this discrete random variable. So that median means that less than that particular value and higher and the above that, the higher than that particular value, both are equally probable as a total. So left hand side total probability is 0.5, right hand side total probability is 0.5, that midpoint is your median. Now what we are discussing in case of this normal distribution. So when we say that this is a normal distribution having a completely symmetric distribution, and it is having some mean here. So in this case you see that exactly at that particular point where it is touching the peak, being the nature of the symmetry, this is covering the total area 0.5. So this is your mode. Now if you take that, so if you take that integration, take that mean, then you will see that exactly this point is becoming your mean, and being this is the highest density point, this is the same point is your mode. So for the normal distribution, the mean, mode and median, this is that where the 50% probability is covered, that is called the median. So for this normal distribution, this mean, mode and the median are same point for this symmetric distribution, that is a normal distribution. So this is meant here that the mean, mode and median are each a measure of central value of the random variable. The mean, mode and median of a random variable x are conventionally denoted by this x bar, which is mean, this x tilde, which is mode, and x m is the median of that particular random variable x. If the PDF of the probability density function of a random variable is symmetric and unimodal, obviously which is the normal distribution, it is symmetric, it is unimodal, that is having only one mode, then the mean, mode and median coincide, just what we discussed just now. Now the second descriptor of this random variable is the dispersion. So dispersion, what is meant is the spread over this mean, that is I know once I identify where it is tending towards the central, I want to know how it is distributed about that mean. So the dispersion of a random variable corresponds to how closely the values of the variate are clustered or how widely it is spread around the central value. In the following figure, if we say that this is the x1 and x2 have the same mean, but their dispersion about the mean is different. So this one, obviously this one which is for this x1, that is fx1, this is the less dispersed compared to the other one which is that fx2. Now how to measure this one, that is this measure of this dispersion. There are generally we use three different measures. The first one is the variance, which is denoted as sigma x square, standard deviation sigma x, and coefficient of variation CV. Now the variance, if we see that variance, which is generally also denoted that VAR of x, of this random variable x, is a measure of the dispersion of the variate taking the mean as the central value. Now when we are measuring that spread around the mean, out of these three central out of the three measures of central tendency, if we pick up the mean and then if we calculate how it is spread around that mean, then that is known as the variance. For a discrete random variable x with PMF Px x, the variance of the x is, this variance is equals to summation of xi minus mu x, that square, multiplied by Px x. So, this is the measure of this variance. I will just explain how these things are meant with the context of this area, with the context of this moment, how it comes. Now, this mu x, as I told, mu x is nothing but the expected value of that particular x. Now, so let us first complete this one before I go for the spectorial representation. So, this is for the discrete random variable, and this one is for the continuous random variable. Now, if the continuous random variable x having the PDF of this fx x, then the variance of x is the x minus mu x, which is the expected value, that square multiplied by fx dx. This gives you that that variance of x. Now, there are some if we just expand it a little, then we can come out to this one. Just we expand this particular value and take this one as this, that is that it will come that x square multiplied by fx dx. Now, you just recall that that expected value of the function. Now, here the function is x square. So, function is x square multiplied by fx dx, which is nothing but the expected value of x square. This is the function of the random variable, which is the x square, minus 2 mu x. Now, this is constant when we are taking this one. So, this is already known, this is constant. So, the 2 mu x can be taken out. So, 2 mu x multiplied by x fx dx. So, x fx dx is nothing but that expected value ex, plus this is again the constant. So, that is plus mu x square. Now, after just doing this, so then again this ex is the mu x. So, minus 2 mu x square plus mu x. So, this is ex square minus mu x square. So, variance can also be represented like this. So, the standard deviation is the another measure of this measure of dispersion, where the standard deviation sigma x is expressed as the positive square root of the variance fx, which is the square root of this variance of x, and the coefficient of variation Cvx is a dimensionless measure of dispersion. It is a ratio of the standard deviation to the mean. So, the Cvx is equals to sigma x by mu x. Now, from this, for all other higher thing, that is the first, how it is becoming the higher thing, that I will just explain in a moment, explain it here. That is what we are doing when we are measuring this, that spread, that is the spread around this mean. What we are trying to take is that first what we are doing, we are taking, this is our mean, and we are taking that x minus mu x, that is a particular value x. If I take that minus mu x, suppose that this is somewhere here, where is the origin is here. So, I am taking the value x here, this is your x and this is your mu x, that is I know that this is your mean. So, I am taking the x minus mu x, that is nothing but from the distance from the mean to that particular value. Now, this one I am just multiplying it with that particular density at that point, that is the dx, and multiplying that one with that distance to this one. So, this is a kind of the second moment from starting from this mean of that particular distribution. So, we will see in a moment how it can be how it is represented as the second moment about this mean, and we can go for this. So, the mean is nothing but the first moment with respect to the origin, and variance is the second moment with respect to the mean. Now, like that I can go to the third moment with respect to the mean, fourth moment with respect to the mean, fifth, sixth, in this way we can go, and each and every moment will give some property of that distribution. For example, the second moment, that is this one with respect to this mean, is giving you the measure of the dispersion, how it is dispersed around the mean. So, we will come that one, how it is represented in case of the mu particularly. So, before that we will see So, here that this distance square multiplied by this this density, that is fx multiplied by this this dx, or the small infinitesimal small area. Now, if I want to know the sample statistics of this measure of dispersion, the sample statistics of the variance is given by, so this sample statistics means again for the random variable some observations are taken xi, for n if the number of samples are n, then xi minus x bar, which is the mean of that particular that if the mean of that sample mean, that minus this one square, summing up them and divided by n minus 1. This n minus 1, this minus 1 is due to the to make this estimate as unbiased. The sample statistics for the standard deviation, as we told, that this is the positive square root of this variance. So, this full quantity power half, that is square root of this one, which gives the standard deviation. For the standard deviation, we go for this first root, but for the higher moments, when you go for this measure of that skewness and all, we generally do not take that the third root of that one to this one. This is here for the first one, that is for the measure of variance, we take the root just to see that if you see this expression, then you will see that the unit of the standard deviation is equal to the unit of the random variable itself. So, this is sometimes a great help. So, that is why we take that one square root and we declare that one as a standard deviation, which we do not do for the higher order moments. And the sample estimate of this coefficient of variation is the sample estimate of this s, and this x bar is that sample mean of this to get that coefficient of variation. So, one example problem we will take for this thing, that is whatever we got the mean and the standard deviation and variance. So, the time between the same example that we discussed in the context of the CDF, that time between two successive rail accidents can be described with an exponential PDF, that is ft t equals to lambda e power minus lambda t, t greater than equal to 0 and 0 for this other areas, that is less than 0. The PDF and CDF we have seen it earlier, that is how it looks, that PDF and CDF in such cases. So, we have to find out the mean, mode, median, coefficient of variation. So, whatever the statistics we have seen just so far, we will just see how it is for this exponential distribution, how it can be calculated for this kind of distribution. So, so this is the PDF of this t, which we have also seen that this value is lambda, and it is gradually coming down and getting asymptotically to this 0 at infinity. So, this is the PDF for that random variable t. Now, the mean of this time between the successive events of this rail accident, if this is the distribution, then we know that mu t, which is the expected value of this t, is the over the entire range of this PDF, the t multiplied by lambda e power minus lambda t dt. If we just do this small this integration by parts, then we will see that this mu t is equals to 1 by lambda. Now, here one thing you can see that so this is that lambda that we are getting here, and again we have seen that the sample estimate. So, if we take some sample of this particular event, then if we calculate their mean, the sample mean, and if we take the inverse of that sample mean, then we will get the measure of this lambda. So, this is how means this is called the method of moment to get that estimate of these parameters. Just few slides before we are taking that how to estimate the parameters. It is one of the method that even how to get that one, but that is not the context what we are discussing here now. We are just getting that for this distribution what is the mean. So, the mean or the expected value of that random variable is 1 by lambda. So, this mean t bar mu t is 1 by lambda. From the PDF, it can be observed that the probability density is highest at t equals to 0. So, the density values, if we see, if we just look this density value, so we see that at t equals to 0 itself, this value, the magnitude of this PDF is maximum, which is lambda. So, from the definition of the mode, we can say that a mode, that is t tilde, is equals to 0. So, mode is at 0, mean is at 1 by lambda. Now, we will see where the median is. So, median means we have to calculate that we have to integrate this one and get some value where it is covering the 50% of the total area. Total area is 1, we know. So, 0.5 we have to integrate it from the 0 to some value x, where it will be equal to 0.5 to get the median. So, exactly the same thing is done. So, the 0 to Tm, that is the value of this median, of this value should be equals to 0.5. So, if we do this integration, we will get that the mean becomes the Tm equals to this, and Tm equals to 0.693 mu t, that is 1 by lambda, the variance of this t. Now, if we want to get that variance of that one, so again we will use that same expression, that is the x, that is the random variable, the t minus 1 by lambda. So, 1 by lambda is nothing but we know that this mean, that is expected value of this t. So, if we take that t minus 1 by lambda square, then multiplied by this probability density dt, then we do this integration by parts, and we see that this sigma t square, which is variance, is equals to 1 by lambda square. So, we have seen that this mean is 1 by lambda for this exponential distribution, and the variance is 1 by lambda square. Now, the standard deviation, again we know the standard deviation should be the positive square root of the variance. So, the standard deviation is again equals to 1 by lambda. So, standard deviation, the magnitude of the are same, the mean and the standard deviation, which is again that 1 by lambda. So, the coefficient of variation, if we want to calculate coefficient of variation of the exponential distribution, is equals to sigma t by mu t, we know that. So, this is 1 by lambda by 1 by lambda, which is equals to 1. So, coefficient of variation is equals to 1. So, there are two other measure of dispersion, and one is that measure of skewness, and other one is measure of pickedness, and we will see this one later. So, these are the higher moments. What we have seen today is that how the first moment about the origin, and in the next class as well, what we will see that we will see that how it is becoming that mean from this. So, one particular distribution if we take, and how these moments are actually coming from this one with respect to the origin. So, this is basically your mu x, how it is means the moment with respect to the origin, and the once we get the moment with respect to the origin, that means we are getting the value of mean, and all other higher moments we calculate with respect to that mean. The first that we calculate is that with respect to the mean, that is the second moment with respect to the mean, what we got, that is called the variance. One open question that I can put before I conclude today's class is that, as I told, that second moment with respect to the mean is variance. What is the first moment with respect to the mean? So, the first moment with respect to the mean, that means I have to take that particular value minus that mean, multiply that density, and that will get. So, interestingly, or this is mathematically very easy to state that the first moment with respect to the mean is always 0, because you are basically whatever the positive side of that mean and whatever the negative side of that mean, both are cancelled out to results in that the first moment with respect to the mean is equals to 0. So, we start with the second moment. The second moment is the measure of variance, third moment skewness, fourth moment pickedness, like that. Fifth moment, sixth moment are there. Basically, up to the fourth moment is sufficient to describe a particular random variable. Today's class we discuss up to the variance. Next class we will start with the description of the skewness and the kurtosis, and we will also see in more details how this can be related to as a moment. So, that will be the starting of again for the first moment and that moment generating function for that for a random variable. So, thank you for today's class.